We are really happy that you accepted the invitation. I believe that your experience and the work that you have done so far is a perfect fit with the main topic of the conference, which is process control and everything revolving around it. So again, thank you very much for coming here, and we are very much looking forward to your plenary.
Thank you very much for the nice introduction. I first would like to thank the organizer, and in particular Miroslav Fika, for inviting me. And at that time, I did not realize that I was coming to this place, and I realized this is such a magnificent place, so magnificent location. So thank you very much twice, let's say, just not only for the invitation, but for inviting me here. My talk is about state observers, and I call it a personal perspective. And so I've been working, let's say, in state observation from the very start of my PhD. This dates back from a number of years now, but then, okay. Anyway, and so my main motivation, let's say, when I started to work on that, it was very specific perspective, let's say, because I was not, let's say, looking for new observers in some sense, but observers that can handle typically model uncertainty. Because this is typically the main challenge that we have to face with reaction system in the large sense, chemical processes, biochemical processes, and so on. And so this is clearly one of my main motivation. So I decided to make my presentation in two parts. First, going back to, let's say, classical observers, and maybe for some of you it will be standard, but maybe in some ways you will have another, let's say, perspective, which is my perspective with also classical observers. And then I shall come up with 5 alternatives to classical observers, and I made a selection. I could have made, let's say, probably 20 or more than that, because I have such a large number of publications on that, and some are very interesting. And so I tried to concentrate on only 5 of them, and 2 are very recent. And maybe I could have put a 6th one, but then I'm not yet ready to present it. I decided to remove, let's say, most of the proofs, just to concentrate on, let's say, the main, let's say, aspect of the observers. And I decided to take one example throughout my presentation, which is a simple microbial growth system, okay? Except in one case, but then you'll see why. Okay, so let's start with my presentation with the basic observer structure. I guess that for those who are not, let's say, familiar with observers, it may be good to understand what it is. Assume that you have a dynamical system, dx over dt is equal to f of x, okay? And you measure some variable, and I call it y, and it's related to the system by h of x. And then my state observer is simply a replica. Where is it? Where is the... is that the one? Okay, yes. Is a replica of my dynamics plus a correction term. This is standard. Even if people like Laurent Prali says that it's not necessary to have the correction term. And okay, anyway. So this is standard, okay? And so in that case, x hat is my state estimate, and the challenge is to let's say, compute the observer gain. So what we know is that in case of a system which is observable, we know that we can find an observer that will reconstruct the unmeasured state with an arbitrary convergence rate, of course, in absence of model uncertainty. That's clearly the idea in that case. Okay, so let it put in the context of reaction system. Okay, chemical and biochemical processes, for instance. And what I say is that in that case, I can always write my dynamics in a matrix form like that, when x is related to the components. It can be also the temperature if you use a non-isothermal reactor. And then typically you have a dilution, let's say, term. You have a, let's say, transformation term, okay, it's where R of x is the reaction rate, and K is a stoichiometric coefficient matrix. This is the inlet term in terms of feed, and this is the gaseous outflow rates. So in that case, typically in that case, you measure a number of components, so relate it with a matrix L, which is composed of ones and zeros. And typically, you need to have a number of measurement which is larger than the difference between the number of components and the number of reaction. And then the observer looks like that. So far, so good. Okay? Let's take the case of the Leuenberger observer, extended Leuenberger observer. In that case, it's probably important to remind that because we are working with, let's say, a linearized version of the computation of the gain, we have to make sure that we fulfill this kind of condition. Okay, so we need boundedness of the, let's say, aerodynamics and of this time derivative. Sometimes people forget that. And so what people never forget is to compute, let's say, the gains such that the dynamics is stable, asymptotically stable. Okay, so in that case, in our case, the linear tangent model state matrix is computed from my general dynamical model. Okay, let's look at the Kalman observer. So for many years, I was struggling with trying to understand what was a Kalman filter. People always come with, let's say, a stochastic version. I don't understand stochastic system personally. I mean, hardly understand it. Up to a point that I realized that it's only an optimization problem. And it's probably for us, let's say, for process control perspective, it's probably better to understand it like that. In that case, assume that I want to minimize a weighted value of the square error, in that case, over a time horizon, okay? And then typically, let's say my gain will be the solution of this minimization problem when R of X is the solution of the differential Riccati equation in that case. So in that case, it's not the algebraic equation that you need. You have to look at the differential Riccati equation for that case. So this is standard, that's in that case. But then in that case, this is not a stochastic problem. It's a, let's say, deterministic problem when you have to find the solution of an optimal problem. Okay, let's look at how it comes in that case. So if I take a simple example, as I told you, I have one reaction, okay, substrate giving biomass. And in that case, for the time being, I consider that the reaction rate is not a mono model, but a contour model when I have this dependence of X, okay? Let's say ecology, for instance, is called a density-dependent model, but this is another story. In that case, this is how it looks. Let's say my state observer like that. And I have to select omega 1 and omega 2 in that case. How do I do that with my Leuenberger observer? I want to have, let's say, second-order dynamics for my observer. So I select lambda 1 and lambda 2 a priori, and I obtain omega 1, omega 2 by solving, let's say, the characteristic polynomial equation in that case, okay? Rather simple, okay? Except that I have to account for the fact that I have the estimates of my reaction rate in that case, or typically the derivative with respect to X and the derivative to the respect to X in that case, but it's a value, sorry for that. It's a value which is depending on the value of the estimate at time t, okay? If I do that locally, I can guarantee that I will have good convergence property. Okay, this is exactly what I have. And if I change, let's say, the value, so if I move the gain to higher gain values, I have faster convergence, okay? Fine. If I look at my Kalman observer, it's a little bit different. And note that I call it Kalman observer and not Kalman filter, okay? My Kalman observer, I have to compute 3 differential equations that I directly obtain from my Riccati equation. Okay, same as is here. In this case, you change the initial value of the the matrix R, and you have faster convergence with higher initial values. Okay? So far, so good. Okay. But as I say, there may be some limitation in this classical observer, and I at least identify two. One is the sensitivity to model uncertainty, and the other one is probably less known, but then people who are working with observer, let's say, they probably face the same typical situation when they simulate the observer. Okay, let's try to illustrate the fact that it's sensitive to model uncertainty. Once again, microbial growth. Okay, I measure X for the time being, and I want to estimate X, and I measure S. Okay, and I have not contour kinetics, but monokinetics. Okay, and so I have a Leuenberger observer that knows the kinetics model, and I select two observer gates, and I make errors, so for slow and fast, and I assume that I have error on the parameters of the mono model in the observer. So typically in that case, I have an error on mu max, so 10% error. What's happening? So let's say with the slow, observer, I have almost convergence. But if I zoom, there is still a bias. And if I even increase the gain, let's say the bias is increasing. Okay? So typically, I mean, we can be safe if we have low gain, but sometimes we don't like to have low gain because we would like to have a fast convergence of the estimates. So, okay. And so this is typically what we have here. I mean, this is for the measurement, but typically I don't care. This is what I care about is really about the X that I want to estimate. Okay, and I do the same with, let's say, Ks in my mono model, okay? The saturation constants. And I have exactly the similar situation. Big bias with large gain, okay? Okay, so this is something that I would like to handle. Okay, this is really, that puzzled me from the very beginning when I started to use state observers. The second thing is what I call the influence of the zero dynamics. Typically, this is the kind of situation that happens. You increase the gain, and at some point, you see that you degrade the dynamics. You typically have let's say, a high value here, and then you slow down the convergence. Where does it come from? It simply comes from the fact that you have relative degree 1 system with zero dynamics in that case. So in that case, assume, let me write say, the equation in that case. I hope that you can follow what I want to see. I write the aerodynamics in this case, and this is typically what I have. So this is exactly the model I had before, the omega 1 and omega 2 here, and it's E1 and E2 and the 2 error for the first and the second state variable. And if I could compute the transfer function between the unmeasured output and the initial value of the state variable, this is exactly what I have. I have zeros, and the zero depends on the initial condition. Of course, we don't know E1 because E1 is X1 is unknown. We don't know. But the idea is that what people forget to do in that case to improve the dynamics is to use the other error as, let's say, design parameter. So I just wanted to show you a very simple example. In that case, when I change the initial value of the error on the measurement, okay? Sometimes people use, let's say, they put it exactly the value that is the measured value, but it's probably not a good idea. If you want to improve the dynamics, in that case, you have to play with that, okay? And if you play with that, as you see, you can easily improve the convergence of your observer. Okay, so far so good. I've stopped with the first part and I go to the second part. Okay, some alternatives. And I start with my favorite one, which is probably the oldest one, but it's still my favorite. Asymptotic observer. So it is based off the general dynamical model that I presented before. And the main idea is that it's based on the notion of reaction invariance. So as chemical engineer, you should all know that if you have the dynamical system of, let's say, a reaction system, you will always have, let's say, the fact that reactions are a constraint. Okay, so you constrain, let's say, the value of your state variable because, let's say, because of the reaction. A given B would be, means that if you consume 1 mole of A, you produce at the same time 1 mole of B. This is a constraint. So behind that, this is the notion of reaction invariance. So it would be a mathematical invariant if, let's say, the system is closed. Okay, let's say batch reactor. Okay, because in that case you have exactly the dynamics which is exactly equal to 0, and so you constrain the system on a specific surface. Okay, so in that case, what is important to see is that the reaction invariance can be, let's say, formalized by using this type of transformation. So I make a partition of the state. I have X, so I partition it as XA, XB, and I compute Z with A0 here, and A0, okay, is the solution of a matrix equation in that case. And if I use that, then I can rewrite the dynamics of the system independently of the kinetics. This is exactly the notion of reaction invariant. Okay, and this is great because then I can use that to reconstruct the state. Because now assume that I have a measure component that's called x1, and I rewrite Z as a function of what I measure, x1, and what I do not measure. And then I have new matrices A1 and A2. Okay, so I know these dynamics, and I have this relation, and then this is what I have with my asymptotic observer. So I compute Z, and then I inverse the relation of Z by putting in evidence, let's say, x2. So I compute the estimate of x2 from Z and the measurement x1. And of course, this is the general case when you have A, which is an inverse, but it can be a left inverse, and I show that in a few seconds, okay, in that case. So in that case, what is nice is that, okay, K, of course, is full rank if you have independent reaction, but if you have reversible reaction, you can consider that as one reaction, and so you're safe. So in that case, you have to, K must be full rank, and you have to select a submatrix K1, okay, the one related to the measure component, such that it is full rank, which means that you need to have a number of measurements that are independent. Okay, there are some cases. I don't know if some people are familiar with biochemical processes when you have the respiratory quotients. Okay. You know that respiratory quotient? Is that familiar to some of you? Respiratory quotient is a ratio of the CO2 produced over the oxygen consumed. Okay, so if the RQ is fixed, let's say 1, let's say, then the measurements of CO2 and O2 are not independent. Okay, this is the case that you cannot use both. You have to use one of the two and not both. So this is, I mean, this is one of the tricky things that you have to face from time to time. Okay, so in that case, what is important, I truly insist on that, is that even if I don't have no correction term, I can guarantee the convergence of my estimate to its true value. Okay, and it is based on this, let's say, if I compute the estimation error, this is exactly what I have in this case. D is generally positive, but I only need this condition which is known in adaptive control as a persistence of excitation condition. So I need to have D different from 0 from time to time. Okay, and it is enough to guarantee the convergence. Okay, so what is great in that case is that I'm completely independent of the knowledge of the kinetics. Whatever the kinetics, I can guarantee that my observer will converge. And I've been so successful to apply it in, let's say, in many applications that for me, this is still my best reference with respect to that. Okay, example. And then I show you why I use this left inverse. Assume that I have two reactions, S1 given X1 and S2, so one biomass X1, and S2 is now the reactant for the second reaction that produces X2. So this is my state vector. This is my stoichiometric coefficient matrix. In that case, I make this partition. Why not? I mean, in this case, it's very easy because if I look at K related to that, the one is identity matrix, 1, 0, 0, 1. Okay, and XB is exactly that. So Z is simply this, obtained by my relation. Okay, assume now that I measure X1 and S1. So A1 will be this, A2 will be this, and my inverse, my left inverse is exactly my inverse, which is computed as follows. Assume that now I have 3 measurements. S1, it should be S2, sorry for that. S1, S2, X2, okay? So this is A1, this is A2, and now I have a left inverse, which is a pseudo-inverse in that case, but then in that case is exactly what I have, and I can use that for computing my estimation. Okay. An illustration, one of the many illustrations that I have, but then, okay, this is related to the production of antibiotics, and so you have these 3, you have the biomass here, you have phosphate with one of the reactants, and you have the products, so the antibiotics here. And it is based on the measurement of oxygen in that case, only the oxygen. As you see, I mean, it's a very nice case of application. Let us move to another example observers. At some point, I had the idea that why should I not use the model parameters that I do not know very well as design parameters? And that was the idea. So once again, simple microbial growth, okay. But in that case, I assume that I have linear kinetics. It's called Blackman kinetics, so alpha between mu and S in that case. And what I say, I would like to select alpha, so I don't know alpha very well, and I select alpha such that the estimation of error on X is equal to 0 in steady state, at least in steady state, okay? So how can I do that? So these are my model equation, okay? So this is my specific growth rate, alpha S, both cases. And I have my observer equation with omega 1, omega 2. And I have 3 design parameters, omega 1, omega 2, and alpha bar. And so omega 1, omega 2, I use it as I can do with a Leuenberger observer, okay, to assign the observer dynamics. So lambda 1 and lambda 2 will be the poles of the observer dynamics. And I shall use alpha bar to handle the model uncertainty. So this is typically the same relation that I had before, okay? And I had this relation. And this is computed from the fact that I fix the steady state value of X to 0, and then I can obtain a value of alpha, okay? Which is reduced to this simple relation if I use double poles, this very simple relation. Okay, so can I guarantee stability of that? And that's what's the key idea. So in that case, this is my observation error, which is given by this aerodynamics, where it is linear with respect to the state, and I have an input term, which is this one. But this one I can show that it is bounded, okay? So I can show that A is asymptotically stable if I have this value of lambda 1 and lambda 2 fulfilling these 2 inequalities, okay? And so typically, I mean, in that case, I can, of course, show you that there are a number of extensions of that. The reverse situation, I let's say measure X and I estimate S, and I have a different value of alpha. But also use this for other kinetics models, let's say for monokinetics. For instance, let's say K bar, Ks, so the saturation constant. And in that case, I would K bar S, which will be given by this expression, okay? So in that case, this is exactly what I have. And typically, this is exactly what I have. I can guarantee that even if I don't know alpha, and I use alpha bar as a design parameter, I will converge, S will converge to its true value. There's a price to pay, but I don't care. The price to pay is that I have a wrong estimation of S, but I don't care. I measure S, okay? Okay, so this is the idea. So I shall go on with another one, which is interval observers. So the idea of interval observer is to say, okay, we have some uncertainty on the parameter. But, so can we use this notion of uncertainty in the design of the observer in such a way that maybe if we are good enough, we will be able to reduce this uncertainty. And that's the idea of the interval observer that I show you now, okay? So the assumption is I have, let's say, a number of parameters theta, which are bounded with lower bounded, upper bounded, as follows, okay? So the idea of the observer, interval observer that it will provide bounds on the state estimation, which is based on these uncertainty bounds, okay? Of course, to design interval observer, you need some good mathematical properties of the system. And this is known as cooperativity. So it's really related to the positivity, let's say, properties of a system. And typically, this means that if I have a system dx over dt is equal to f of xu, you need to have, let's say, a Jacobian where the off-diagonal terms are positive. Okay? Okay, once again, simple microbial growth process. We say that mu, so the specific growth rate is bounded, okay, lower and upper bounded. We measure S, we want to estimate X. And so when you use the model in original format, you see that it will not work, because if I look at the observer equation in that case, the Jacobian is as follows. And in particular, this off-diagonal term is always negative. So once again, that's where my reaction invariant notion is interesting, because then I can rewrite the system by using the straight transformation that I used before in this specific case. Z is equal to x plus s over k1, the yield coefficient, okay? And then I can rewrite the dynamics of my system not with respect to S and X, but with respect to Z and X. And this is my state observer in that case. So if I look at my Jacobian, typically if you look at the off-diagonal term, okay, it will be cooperative. My observer will be a cooperative if omega 1 is positive and omega 2 is negative. Okay, that's the idea. Okay, maybe I should tell you why it's important to have this cooperativity condition. I forgot to mention that. So the notion of cooperativity means that if you start with two initial conditions, let's say with the same system, if I may say it like that, the trajectories never crosses. Okay? They always keep, let's say, in the same direction, they never cross. So that is important. So I can guarantee in that case, that's why cooperative is important. In that case, I can guarantee that if I estimate, that's what I shall use now with my interval observer, I will have two observers, one for the upper bound and one for the lower bound. So in that case, because of the cooperativity, I can guarantee that the upper bound will remain always above the lower bound. And typically in that case, above, let's say, the exact value of the estimate. Okay? That's exactly what I have in this case. So of course, it looks a little bit tricky in this case. For Z is standard, but for X, I have to use mu plus and mu minus in this case, in case when maybe X plus might be negative, and I have exactly the same. It's look a little bit tricky, but it shows you that sometimes it's not easy to, let's say, design such kind of observer. But what is interesting, if you have used that, and if I look, let's say, at the stability properties of it, as long as I have omega 1 and omega 2, okay, positive and larger than some value for omega 1 and lower than some value for omega 2 negative and lower than some values, then I can guarantee that the estimation error, the upper estimate and the lower estimate, converges to a tube, okay? Which amplitude, which is AX plus and NX minus in that case. And if you look at the value of this AX, you can see that you have omega 1 at the numerator and at the denominator, but omega 2 appears only at the denominator. In other terms, if you choose omega 2 sufficiently large, the tube will converge to something which is very small. So this is great because a priori I have maybe a very large uncertainty of my parameter, but by playing with my interval observer, I can guarantee that I converge close enough to the true value. Okay, this is exactly what I want to illustrate in that case. So we had two cases, for instance, in that case, mono, okay, or combination of mono and aldane, okay, and these are the exact value that we use in the present case. So typically, this is what we have if we change, let's say the value of omega 2, okay, and if we increase omega 2, you see that, so this is omega 1, omega with 1.01, and this is when C2 is larger, so theta is hundreds, you see that my tube is becoming almost imperceptible, okay? It's very small one, okay? And if I do the same, so this is one of the ideas, if I do the same, if I have an upper model, mono model, and a lower aldane model, and I know that my model is in between, okay? I have typically, I mean, this is another type of simulation. I can show you hundreds of other simulations of that. Typically, as you see, I have exactly the same type of behavior in that case where my tube can become small enough, which is great. Okay, so let's move to two rather recent observers on which I've been working. Is one with finite time converging observer. So at some point, I've been working with the Total company. You know, Total is a big petrochemical company, and they had a big problem with trying to guarantee that they can have estimates of the state in polymerization reactor very quickly, in batch polymerization, because then they can anticipate possible, let's say, runaway of the process in that case. And so they wanted to have, let's say, what I call finite time convergence. Guarantee, I mean, the problem with the observer that I've shown so far is that I can guarantee convergence, but it's asymptotic convergence. Sometimes you don't have time to wait. You want to have the exact value very quickly. Okay, and that's why I've been working a lot on this finite time converging observer. And what I show you is one of the observers on which I've been working with Jaime Moreno from Mexico. And so this is based on, maybe some people in this room know sliding mode control, but it's basically around this idea. So it's called a discontinuous observer, sorry for that, discontinuous observer. I mean, it's what Jaime says a super twisting observer, which is the generalization of sliding mode observers. So this is once again simple microbial growth, but I want to handle another issue, which is I want to also estimate the unknown inputs, which is standard in some situation like wastewater treatment, let's say, when you don't know the input, but then you'd like to know it because it's important in let's say, in the optimized management of the plant. So assume that you have three state variables in that case, xs, and I have to add another state variable, which is the input, okay? So the basic idea is to have a state transformation in new state variables based on the observability form, so which will be x dot and x double dot, okay? And typically I need, of course, the inverse transformation to get back to my true estimation, okay, and especially the estimation of S in. So this is the inverse transformation that I have. As you can see, it's not that simple, okay? Anyway. If I do that, so this is typically the Brunowski form, okay, so for my system, x1, x2, and x3, and I have two terms f and j in that case. So as you can see, even in this simple case, I have, let's say, long expression for f and a rather shorter expression for j, okay? It's once again for a mono in that case, okay? So what is the idea of the observer? So what is typical from sliding mode is that you have the sign function, so +1, -1, depending on the value of, let's say, x1 minus x1 half minus x1. But you multiply it by a term which is the absolute values with, let's say, an exponent which is non-integer, okay? Non-integer in that case. And because of that, I mean, typically if you make a Lyapunov analysis in that case and you select this kind of Lyapunov function, what is nice is that you obtain this derivative of the Lyapunov function. And from that, of course, it's a little bit tricky to show it like that, but because of this specific exponent, I can guarantee that I can converge in finite time. Okay? There is a finite time t such that my values of the estimate will be the exact value. The error will converge to 0 in finite time. Okay? And it's really because of that. Okay? It looks simple, but then, you know, at that time, it was the first time that Jaime, working with me, was coming with the result with a third order system. Okay, so far he had result with second order systems. So for the first time he had that with third order system. It's very complex, and that's why I wanted to avoid the proof with respect to that, but I can give you the paper if you're interested. And it's very fascinating, okay? This is typically the simulation that you obtain in that case, and that just to show you have really convergence in finite time, okay? And especially for S in. In that case, we had variation of S in, okay, in that case, and you see that after time, at this time here, it's exactly on the true value of S in, okay? Of course, there's a price to pay, as everywhere. This is extremely sensitive to noise, okay? In that case. But this is fantastic. Imagine the situation. I have a system from whom I do not know one of the input. And this input is changing with time. And I'm able to get the exact value of this input after a finite time. And once I'm on it, I will not go away. So for me, this is really a really fascinating result. Even if I know that I have some price to pay, and I mean, I know that you know, there are still work that I done to improve, let's say, the robustness of this kind of solution. But of course, it is something which is very interesting to see. Okay, the very last example is a work that I've been doing with Alain Rapaport from INRA in France. And so it's a very specific case. It's case when you have systems that are not observable on their boundary. And I'll try to explain what I mean by that. And I mean, we've been working for at least 2 years. So we had the case study of batch reactor in a simple microbial growth reaction. So still the same example. The equations are very simple, okay? And I measure, in that case, the biogas flow rate, which is typically mu x. Okay, for simplifying the notation, I say that the yield coefficient, the stoichiometric coefficient are all equal to 1. Okay, and I don't lose any generality with respect to that. It's just a change of coordinate. And I go back, go back to the initial case in that case. The typical situation that you have to handle in that case is that you don't know the initial condition in batch condition. You don't know them exactly. And this is typical in biochemical systems. Okay? So you want to estimate the total biomass production while you don't know the initial condition. Okay. So once again, my reaction invariance comes back into the picture, and I rewrite the dynamics with respect to Z and S in that case, which will be exactly this. So dZ over dt is exactly equal to 0, okay? This is my reaction invariant in that case. I'm in a batch reactor, so closed system. And this is my output. And if I make an observability analysis in that case, so this means that this map has to be injective. on the cone where z larger than s larger than 0. Okay? But on the boundary, so at the limits, when times goes to infinity, you have no more substrate. The reactant is consumed. Okay? So this means that s tends to 0. So if I use, let's say, Lie derivative, okay, to compute, let's say, to compute my observability test, this is exactly what I have. And I have mu of s, for instance, here. And mu of s is equal to 0 if s is equal to 0. Monomodal and things like that is always like that. No reactor, no reaction. Okay, we all know that. Okay, so this means that on the boundary, so when s is equal to 0, I have a loss of observability. How can I design an asymptotic observer, I mean an observer that will converge asymptotically, if I have at the end a point for which I don't have observability? And so this is the problem that we wanted to handle. And this is the solution that we have. It took us almost like 2 years to get to that. And this is a simple version. I have a more complex version that I'm not going to show you because you are going to kill me, I'm sure. So this is the simple solution. So the solution is to have, let's say, an equation of, let's say, the time derivative of y, so which I call v dot, okay? And v initially is equal to 0, and estimate x, okay? So remember, maybe I should go back to that, but remember that x is, maybe y, okay, let's see. Y is mu x, y is mu x, okay? Otherwise, x is y over mu, okay? Let's just put like that, okay? This is clearly what I use in that case. I use this property in this case. So this is my observer. Because if I do that, x hat is y over mu, okay, plus a term which is related to the integral of y of t. And if I compute the aerodynamics, okay, this aerodynamics is negative everywhere. This means that I can guarantee then x hat will converge to x, okay? So once again, I come back with an observer, and I call it an asymptotic observer in that case, that converges. I don't have any correction term, but I use what I know about the system dynamics to guarantee its convergence, even if I have a loss of observability at some specific important point. Okay. So just end up with some simulation with respect to that. So we use a number of, let's say, models like, let's say, mono, IL, which is not concave, and aldane that you've seen before, non-monotonic. Okay, so this is typically what we have. So if I use a Leuenberger observer, I know that I will not be able to converge. Okay, and this is exactly what I have here. I have here. So this is the true value, black, and the observer will not be able to converge. I will have a bias, whatever happens, because of this loss of observability. I can do, I mean, this is the best, I tell you, this is the best Leuenberger observer that we have, okay? We didn't try to show you, oh, I put wrong, let's say, condition for Leuenberger. No. This is the best solution that you can have with a Leuenberger observer. And so then we have our asymptotic observer that converges exactly, okay? And so even if we put, let's say, noise on that, we still have the same convergence. I mean, in that case, because of the noise, it's a little bit more tricky. So we are not able to convert exactly to the value in presence of noise. But then we do a much better job than the Leuenberger observer. And we have the same with, let's say, IL model and with the aldane model. Okay. So at this point, let's say I would like to express my deepest thanks to two of my best colleagues and friends, Alain Rapaport from INRA Montpellier in France and Jaime Moreno from the UNAM in Mexico. I mean, so I had such a great time to discuss with him, discussing about these observers. These guys are so great, so spending hours writing crazy stuff on the board, and then coming up with, let's say, sometimes crazy solutions, sometimes fascinating solutions. So it's great to be able to, today, to be working with these people. So thank you very much, and I'd be happy to answer any question that you may have. Just to tell you that I have a second life. I am a rugby coach. This is my, I'm a rugby coach of a ladies team. So actually that's what happened with, after the match, when the ground is muddy, let's say, and they love that. So thank you very much.
Thank you very much for a very interesting talk, which to me gave a very useful overview of an area which is very important, state estimation. We have time for questions, please. Brother.
So many times in your presentation you were kind of seemingly ignoring the noise. Then you mentioned it at the end, but I was actually wondering, like, do you suggest that, for example, Kalman filter takes the noise into account directly in the design of the filter and works out the filtering? So do you also suggest that if you have these nice properties of the estimators or observers that you showed, that we should deal with the noise somehow offline, like to have kind of averaging filter, some sort of a filter which deals with the noise separately? We shouldn't consider it in the design.
My strong belief after so many years is that noise, measurement noise, is not an issue in process control. Like it is in more, if you work in electrical engineering and mechanical engineering, the noise is much more, let's say, present, let's say. In our case, it is not really an issue. The issue is not there for me. The issue is really in somewhere else, typically in the modeling error. And that's why I want to concentrate on that. And I strongly, my experience from practice is that whenever I had to apply it, it's very simple to, let's say, to get rid of the noise, let's say, by some good filter. And it's usually much enough. I don't remember to have to face a situation where the noise was such that I couldn't, let's say, apply what I did, let's say, in an efficient way. But this is my strong belief. And what you said about Kalman filter, you say Kalman filter, I say Kalman observer. And for me, this is a different perspective. Of course, there's something which is nice when you apply a Kalman observer, to use, let's say, the covariance of the state variables as the initial value in your Riccati matrix. That's nice. That's a good way to handle it. There's a nice paper an old paper by Christos Georgiakis who's stating that, and this paper is great. But apart from that, this is the only thing that we retain from the Kalman filter, let's say, as applied to process control.
Okay, it's almost related to the same question as well. In all the methods that you explained, you always show a strong characterization of the system.
Yes.
So this work with some weak relation, because all the dynamics, for example, in the asymptotic observer, in my opinion, there is always a correction because X2 is finding based on the correction of the system based on this transformation. So I think that the accuracy of the model, in your case, in all your observer, is really important. The accuracy of the whole system.
But don't be confused. The accuracy that I need is the reaction scheme. The only assumption that I need is to have a reliable reaction scheme. I don't care about the rest. I don't care about the kinetics, typically. Probably I should have insisted on that, but my main model uncertainty is in the kinetics. And basically, this is what I try to, of course I concentrate on methods that do that. Concentrate on how can I handle typically uncertainty typically in the kinetics.
Okay, and I have another one. You show many observers where depend on one transformation of the state. and after that I have to go back to take my state. This is a drawback, or how do you see this point? Because in my opinion, I'm not so smart, so I cannot find this transformation easily, and I need to understand really well the model to make this smart transformation. There is no a general way to find the observer.
Okay. So probably for the last one, it will take me some time to explain. For the last example, that's the kind of transformation that we use, because I must admit that it took us 2 years to find out the right transformation, and still I'm not able today to really have, let's say, the intuition with respect to that. The one that I use the most is the reaction invariant, but that's on the floor for so many years. I mean, I did not invent the reaction invariant. I mean, I started to use the reaction invariant without knowing that there was reaction invariant. And at some point, some guy tell me, oh, but that is a reaction invariant. So what? You know, this. So I look at the literature and I found out, oh, yes, and that was great. But then really the idea, you know that you have a reaction system. I mean, by a reaction scheme. There is always a transformation such that a part of the dynamics is independent of the kinetics. As simple as that. That's a strong structural property of any reaction system. And you don't need to, I mean, this is simple. Okay, the one that I use for let's say, the discontinuous observer, let's say the finite time converging observer, this is standard in nonlinear system. So you put the system, it's a change of integrators, okay? It's called as the Brunowski form. You open the book of Isidori, of any book, or Khalil, or whatsoever, and you'll see that this transformation, I mean, this is standard, okay? Of course, that's the idea. I mean, Jaime is a strong guy in state observer. So he's probably the best guy in state observer in the world today. And this guy, so he has kind of, you know, he knows what to do. And so intuitively, say, I have my system, I want to make sure that I can observe it, so I put in observability form. If it's really an observability form, then I can apply an observer. This is how he does. So in that case, this is it. So I don't think that I use many other transformations so far. But of course, the reaction invariant is almost everywhere.
Thank you. Further questions? I actually have two. One technical for that observer with finite time convergence guarantees. Can you prescribe this finite time in which it will converge, or is it a consequence of the tuning of the observer?
No, look, formally, you can select the design parameters so that you can guarantee that the finite time will be before this, formally, okay? So on paper you can, but it's more difficult to do that really in practice. So typically, typically what you compute is a bound, in a bound after which you guarantee. Usually it happens before. Okay, but that's okay. I can give you the paper. It's probably not.
Okay, and the second question is, I actually got this question during my PhD exam, which was about optimal control, state feedback control, and the question was, what do you think is more important, good control or good estimation? Of course, at that time, my answer was, of course, control, okay, because I was a young guy, unexperienced.
And you expect me to say the reverse, is that?
No, I just want to learn about your experience when it comes to the combination of the two, because they can never be thought about in an isolated environment.
I probably shall not answer your question, but my answer is different. Initially, I mean, state observer, Leuenberger's observer, Kalman observer, especially Kalman observer, came on the floor because people wanted to have, let's say, good control performance in absence of state measurements. And if you look at that, I mean, people, for a long time, they didn't care about the state observation. What they wanted to have, if you look at the LQ control, typically what people look at is good control performance with or without an observer. I don't measure the state, I make an observer, and I don't care about the observer. What I care about is that control. And that was the initial idea of state observer for me. For a long time, for me, state observation was not done for observing states. It was done for controlling the system. Okay? So that's why at some point, you know, for us at some point it was very important to get precise software measurements of important process components, because that's the situation that we had to face. And so that's why, you know, for me it was an important issue. So for me, yes, an important issue is to have good state estimation in some instances. But once again, it depends on the objective. Is the objective in control? Don't care about the state estimation. Is the objective, if you have good monitoring, then you have to look at good state estimation. There's not only one answer to your question. Okay. As far as I am concerned, at least. I don't privilege one over the other.
Okay, thank you. Are there any other questions? If not, then let us thank Professor Dochain again. Thank you very much.